Hey Global Impact students, this is Mr. Ellinger here. This lesson is on patterns and linear functions. Our learning target for the lesson is we want to be able to identify and represent patterns that describe linear functions. Some essential understanding for you for this lesson. The value of one variable may be uniquely determined by the value of another variable. Such relationships may be represented using words, tables, equations, sets of ordered pairs, and graphs. Some background for the lesson. This lesson extends the representation of functions from graphs into verbal descriptions, tables, and equations. Besides dealing with functions in all these forms, we need to learn that all these forms are essentially the same thing. They all represent some kind of rule that maps a value of an input variable to a value of an output variable. The same rule that generates an equation is the rule that generates a table and a graph. Alright, so in a relationship between variables, the independent variable changes in response to another variable called the independent variable. Values of the independent variable are called inputs, and values of the dependent variable are called the outputs. The value of one variable may be uniquely determined by the value of another variable. Such relationships may be represented using tables, words, equations, sets of ordered pairs, and graphs. So, this essential understanding here, when you connect it to this concept of dependent and independent variables, what that means is that what we say a lot of times is we say that for every input there is one unique output. Okay, and what that means really is, in terms of variables, the most common variable that we use for input variable is x, and our most common output variable is y. So another way to say this would be for every x, there is one unique y when we're talking about functions. So in the diagram below, what is the relationship between the number of rectangles and the perimeter of the figure they form? Represent this relationship with using a table, words, an equation, and a graph. So here we have one rectangle, and it has length of 6, another side length of 1. Here we have two rectangles put together, and we have, they're all the same rectangle here. We're using a 6x1 rectangle. So when we put two together, we have a 6, and then we have a 1 and a 1, and a 6 over here, and a 1 and a 1. And here's what it looks like when we put 3 rectangles together, and here's what it looks like when we put 4 rectangles together. So what we're going to do is we're going to look at the pattern that develops here. For every rectangle we put or add to the figure, what happens to its perimeter. So first step is to make a table. So we're going to use x as the independent variable and y as the dependent variable. So x is going to equal the number of rectangles. That's our independent variable. And we're going to let y equal the perimeter of the figure. Y is the dependent variable, okay? The perimeter of the figure depends on how many rectangles we have. So the perimeter is dependent, the number of rectangles is independent. So we're going to write each pair of input and output values, x and y, as an ordered pair, x comma y. So here in our table we have our number of rectangles, 1, 2, 3, 4. And the way that we calculate the perimeter is we take 2 times the 1 and 2 times the 6. Okay, so up here in our rectangle we have 2 times, in general the perimeter of a rectangle is 2 times the length plus 2 times the width equals perimeter. So whether we call the 1 the width or the length is irrelevant here. We're just going to multiply 2 times the 1, the side length of 1, and 2 times the 6. Okay, so for one rectangle, 2 times 1 plus 2 times 6 is 14. So our ordered pair, one rectangle, generates a perimeter of 14. So that's a 1, 14 ordered pair. When we have 2 rectangles, as you can see from the picture up there, we're going to take 2 times 2, and we're going to add 2 times 6, which is 16. So 2 rectangles generates a perimeter of 16. And so on, 3 rectangles, 2 times 3 plus 2 times 6 is 18. 3 rectangles in the figure generates a perimeter of 18. And 4 rectangles, 2 times 4 plus 2 times 6 equals 20. 4 rectangles generates a perimeter of 20. So you can see here, in every perimeter we have, we're always going to have 2 sides of 6. And then however many rectangles we have, we're going to have that many 1s times 2. Okay, so that's the pattern that's developing here. So if we look at our table, the pattern in the table, describe the pattern in words so you can write an equation to represent the relationship. You know, a lot of times we want to start off in words. What is the relationship? And we may not necessarily have to write it down, but we need to think in our mind, what is the relationship between the two variables here, okay? And what we observe is that, you know, x is changing by 1 every time, increasing by 1, and the perimeter is increasing by 2 every time, okay? So in words, if we multiply the number of rectangles in each figure by 2 to get the total length of the top and bottom sides of the combined figure, then add 2 times 6, or 12, for the total length of the left and right sides in the combined figure to get the perimeter, right? And that's what we talked about here just a second ago. The equation is here. Let me write this out. The perimeter So where this equation comes from, y equals 2x plus 12, it comes from the fact that if we look at the information in our table here, each perimeter is equal to 2 times the number of rectangles plus 12. So 2 times 1 plus 12, 2 times 2 plus 12, 2 times 3 plus 12, and 2 times 4 plus 12. Every single one of these calculations, there is a constant in here. This 2 times 6, this value of 12 right here, okay? So this value right here is a constant. Every single time we're adding 12. What's changing, or what's varying, hence the term variables, is this value right here, this number of rectangles. That's our variable, okay? That's a variable quantity, okay? And then the perimeter is also a variable quantity, so that's also a variable. Okay, so there's one thing that's constant here, and that's the 12. And when you look at the equation, things that are constant or that don't change in any calculation that we do always have just a plain old number. Okay, we call them a constant. So y equals 2x plus 12 is how we would represent the statement that I had written here just a second ago algebraically. Once we have our equation, then we're going to make a graph. So once we have this table of ordered pairs, we can just plot those ordered pairs. So that's what you see here. We have 114, we have 216, we have 318, and we have 420. Right? So that would be the graph of this data. Now this is what's called a discrete graph. It's not continuous, it's a discrete graph. Okay, what that means is that we cannot connect these dots with a line or a line segment. We can't do that. If you think about why, well, if we did, then that would mean, let's say I connected these two with a line segment. If we connected that, what we'd be saying is that every single value between 1 and 2, meaning like 1.5 rectangles or 1.75 rectangles or 1.1111 rectangles or whatever, anything between 1 and 2, we would say we could have a figure with that many rectangles in it as well, but we can't. We're just dealing with whole number rectangles here. So that's why this is a discrete graph, discrete data. Okay. All right. So let's talk about this a little further here. We can describe the relationship in problem 1 by saying that the perimeter is a function of the number of rectangles. Okay. So the dependent variable, we can describe it as a function of the independent variable. Right? That might be a new word for you, function. So a function is a relationship that pairs each input value with exactly one output value. You have seen that one way to represent a function is with a graph. A linear function is a function whose graph is a non-vertical line or part of a non-vertical line. Okay, so just a couple of graphics here to kind of illustrate this idea of a function. You know, and a lot of times we talk about this function machine, okay? So what we're going to do is we're going to take some input variable and we're going to put it into the machine, right? And then inside this machine, the machine does some stuff to the value, right? It might multiply it by some numbers, it might add some numbers, it might square the number, it might take the square root of the number or whatever. But after it does some things to it mathematically, then there's this output that comes out of it. and we call that the dependent variable. Okay, so if a lot of times if we just remember that a function is like a machine, you put something in, you do some things to it, and you get something out. All right. So to give you an example here, let's say that we have this function. We'll talk about this notation here in just a minute, but let's say that this function is the square root of x. Well, if we take an input like, say we're going to put 9 into this function. So we put 9 in, and when we put 9 in, what we have to do is we have to take the square root of 9. Well, what is the square root of 9? The square root of 9 is 3. So what comes out of this machine into this basket here, this would be like a basket catching whatever comes out of the machine, there would be a 3 in that basket. Okay? Give you another example here. Let's say that our input is 25. So we're putting a 25 into the machine. What comes out of the machine? Well, whatever the square root of 25 is, which is 5. Okay? Input and output. Now it gets a little tricky when we have, say we input 17. Well, what's the square root of 17? The square root of 17 is going to be 4.1 something. All right, so even though we're not putting a nice perfect square number in here, we can still take the square root of it. We still get an output value. All right, so the value that comes out of here depends on the value that's put in up here. So this concept of a function machine could be very useful for you at first. All right, let's take a look at another example here. The table shows the relationship between the number of photos, x, you take and the amount of memory, y, in megabytes left on your camera's memory chip or memory card. Is the relationship a linear function? Describe the relationship using words, an equation, and a graph. So here's our table. We have the number of photos, okay, that we're taking, and then we have the amount of memory that's left on our card after we take a photo. So what you notice in the data here, and this is what we always have to look at, this is what algebra is about, the relationship between x and y, the relationship between the number of photos and the memory left on your card. What is that relationship? So as x increases by 1 every time, that's the pattern here, okay, plus 1, plus 1, plus 1. What's happening over here? Well, these values all go down by 3. Okay, and here very soon we're going to discuss this as what's called a rate of change. How is x changing related to y? All right, so there's our observations in the data. What we know is we know the amount of memory left given the number of pictures taken shown in this table. What we need is we need other representations that describe the relationship. So here we have a table representation. We also need to write this in words. We need to write an equation, and we need a graph. And the plan, we need to look for a pattern that can describe in words, to write an equation, make a graph to show the pattern. And so we've identified the pattern. So the amount y of memory left is uniquely determined by the number x of photos you take. So meaning y is determined by x. Y depends on x. You can see this in the table above, where each input value of x corresponds to exactly one output value of y. So y is a function of x. To describe the relationship, look at how y changes for each change in x in the table below. So up here in the table. So again, this is our continuation of our problem here. And like we said, we identify the pattern here. X is changing by 1 every time, a positive change of 1. Right? And the memory is 512 megabytes before any photos are taken. So when x is 0, no photos have been taken. That's kind of like our starting point. Okay, and so the starting point, we call this an initial condition. So we will refer to initial conditions quite frequently. So initial condition is like our starting value. So the independent variable x increases by 1 every time. The dependent variable y decreases by 3 each time x increases by 1. So in words, what we would say is the amount of memory left on the chip is 512 minus the quantity 3 times the number of photos taken, right? So if there's 2 photos, 2 times 3 is 6. So we're subtracting 6 from 512. 3 photos, 3 times 3 is 9. Subtract 9 from 512, we get 503. So that's the relationship in words that's going on here. We're taking 512, and then every time we take a photo, the amount of memory is being reduced. So this is a subtraction situation, okay? So the amount of memory on the card is being reduced every time we take a photo. So this is a subtraction situation. So the equation would be y equals 512 minus 3x. Again, 512 is the constant. Okay, there's 512 megabytes of memory on the card. And then from there, we're going to reduce every time we take a photo. So then we can graph this. So these up here in our table are ordered pairs, and we can plot those ordered pairs. Here's 0, 5, 12. Here's 1, 509. Here's 2, 506. And here's 3, 503. You know, and what we would have to do with this graph is, if we were drawing this by hand, we would have to scale this accordingly. And, you know, a lot of times we start at 0, 0, and then we'll say, well, how do we scale this? Do I go by hundreds? Do I go by thousands? What do I do? Well, the key here is this. See how the vertical axis kind of has this little zigzag in it? What that zigzag means is that we're going to start at 0, but there's going to be a break in the graph, essentially. We're going to start at what our useful values are. So 500 is really like the most useful value. So if we start at 500 and then we go up by 2s, we can get all the data in there. So we'll just kind of show this break in the graph. We won't go, you know, up by 2s from 0. We'll show this zigzag, this saying, all right, there's a bunch of stuff in here. We're just going to kind of disregard that, and then we'll start at 500. And then we scale our number of photos axis accordingly. So remember, independent variable always goes on the horizontal axis. Dependent variable always goes on the vertical axis. Okay, always, always, always. So then our ordered pairs, when we go to plot 0, 5, 12, we start on the horizontal axis with the independent variable, and then once we get over to that independent value, then we go up to the value of the dependent variable. Okay, so we go to the independent variable value, and then from there we go up to the dependent value variable. Okay, so this is kind of our first lesson here with some higher level math. We got some new terminology, but the word function is something that maybe you haven't heard before in the past, but it's something that you're going to hear quite frequently from here on out. Okay, we're still going to use words like equations, but a lot of times we're going to refer to equations as functions. So that's it for now. Hope you guys have a great day.